Okay, so here's our last example from section 6.2, and this one is still going to be approached in essentially the same way, but the way that we go forward with our steps is going to look a little bit different. In particular, we're going to do this without using the summation notation, except for at the very beginning where we say that y is equal to this power series. It's going to be easier in this problem to write our series out term by term. And I know that seems very tedious, and that's because it is, but it actually just makes the problem easier to manage because the stuff that we're going to encounter in this is just too cumbersome to try to keep in summation notation. So you'll notice in this problem, we're doing another second order DE, but now we're not dealing with polynomial coefficients like we have in the previous two examples. In fact, one of our coefficients is the exponential function, e to the x. And the technique for solving this is similar to what we've been doing, but we use the Maclaurin series for functions like e to the x and substitute that in here. That actually turns everything into a power series, which we can then solve the way that we've been doing this. So in this problem, I have a y that's supposed to be a y prime there, and a y double prime. So I'm going to need all three of those laid out. Y, once again, we're going around about the ordinary point x equals 0, and it's easy to show that that is an ordinary point for this. Y will be equal to this series, n equals 0 to infinity, cn x to the n, which means y prime is going to equal this series, n equals 1 to infinity of n cn x to the n minus 1. Y double prime will equal this guy, n equals 2 to infinity n times n minus 1 cn x to the n minus 2. Okay, and then in addition to that, we also need the Maclaurin series for e to the x. E to the x is equal to series from n equals 0 to infinity of x to the n over n factorial. Okay, now in order for this to work, you'll notice we're actually multiplying two series together. I need to multiply e to the x times y prime when I'm dealing with this term right here. But both of those have been expressed in terms of power series. And that's why we did an example practicing the multiplication of power series in the previous section. So before I even start substituting stuff into the larger DE here, I want to just deal with this term separately. Let's look at what e to the x y prime should look like. Okay, so e to the x, and even though all of these are written in summation notation, I'm not going to write anything else in summation notation. I'm actually going to write out terms from these series. And for what we're going to do here, we don't need to go any further than writing them out to the x squared term. So the power series for e to the x, the Maclaurin series, is going to look like 1 plus x plus 1/2 x squared plus ... That's as far out as I need to go. Y prime is going to look like, so here's y prime, starting with n equals 1. That's going to look like 1. And then my next term, oh, sorry, not 1. It's going to look like C1. Let me change that to a C1 because we have these coefficients in here. C1 plus 2C2, x plus 3c3 x squared plus ... And again, only going out as far as the x squared term, it'll be sufficient for what we're trying to do here. Now we multiply these out the way that we have in that one example that we did back in section 6.1. So I take this 1 and I multiply it to each term here. 1 times each of these will just replicate that series. So I'm going to get C1 plus 2c2x plus 3c3x squared plus ... And again, when I multiply these series out, I'm only going to be interested in what the product looks like up to the x squared term, at which point I'll just say plus ... So what that means is this. When I take this x and multiply it to this series, the first term I'm going to get is x times c1 or plus c1x. I want to align it with the other x term here. And then I'm going to get x times this term, which will look like plus 2c2x squared. And then even though I can multiply the x to this term, it's going to produce an x cubed term, which I'm not going to end up using in the end. So I'm not going to bother writing that one, okay? Finally, plus 1/2 x squared times c1, that brings me down to this step here. That's going to be plus 1/2 c1x squared. And then if I multiply that term to anything else, I get x cubed, x to the fourth. I get higher degree terms than I want. So I don't bother writing those because we're keeping this, we're trying to keep this from spinning out of control, being too crazy. So now I'm going to add these up, and this will give me c1 plus 2c2 plus c1x plus 3c3 plus 2c2 plus 1/2 c1x squared plus dot dot dot. Okay, so that's what the first three terms of this series will look like. Now what we need to do is deal directly with our DE. So again, the DE is up here. Y double prime plus e to the x y prime minus y equals 0. What does that look like? Well, y double prime plus e to the x y prime minus y is equal to, now what I'm going to do is, because each of these three terms is a series in its own right, I'm going to stack them vertically. So I'm going to start with y double prime, which we have written up here, but it's in summation notation. I need to write out the first three terms. So plugging in 2, 3, and 4 into that guy. That's going to give me, as you can verify, 2c2 plus, I'm going to give myself a little space here actually, plus 6c3, wish I could erase my pen, plus 6c3x plus 12c4x squared plus dot dot dot. Okay, so this whole thing right here is just the first three terms of the series corresponding to y double prime. Now I'm going to do plus e to the x y prime, which we found the first three terms of that series up here, but again I'm going to stack those. So this is going to say plus c1 plus 2c2 plus c1x plus 3c3 plus 2c2 plus 1/2 c1x squared plus dot dot dot. Okay, that was this middle term right here, and then minus y. So y was this original power series that we came up with in the first place, and it's being subtracted, so these will all be minuses down here. Minus c0 minus c1x minus c2x squared minus dot dot dot. Okay, so again, that's y double prime, that's e to the x y prime, and this is minus y. We want to collect all of these like terms, which is like, you know, evaluating all of this after making those substitutions. These constants will add up to 2c2 plus c1 minus c0. These guys, when I add them up, it's going to look like this, plus 6c3 plus 2c2. And then notice I have a plus c1x and a minus c1x. So those will cancel each other. X. Okay. Now the x squared term. So this will become plus 12c4 plus 3c3, and then notice here I have a plus 2c2, which I'm going to later subtract another c2 from. So that's actually just plus c2 plus 1/2 c1, and that's my x squared term. And then again, there's a whole, you know, series after that that we're not looking at any further. So we're only caring about up through the x squared term here. Okay, this again is equal to 0 from my original DE right here. So this is where I would start to use the identity property. Now, you're not going to solve for C0, C1, C2, C3, all of those explicitly, but we shouldn't expect to. Remember, these are second order equations, and we're expecting two parameters. And in the past two examples, C0 and C1 became those parameters. So with that, expecting that, let's set up this first constant and set it equal to 0 using our identity property. 2C2 plus C1 minus C0 equals 0. I don't need to solve for each one of these explicitly. I just need to solve for C2 in terms of C1 and C0. So I'll add C0 over, subtract C1, and divide everything by 2, giving me this. C2 equals C0 over 2 minus C1 over 2. Okay, so there's C2 in terms of C0 and C1. Now I'd like to take C3 and find a way to put that in terms of C0 and C1. I can use this second term here, set its coefficient equal to 0, so 6C3 plus 2C2 equals 0 implies that C3 is equal to negative 1/3 C2. I don't want that to be a C2. I want it to be in terms of C0 and C1. So I make this substitution here. I can plug that in for C2. And if I did that, negative 1/3 times each one of these gives me negative C0 over 6 plus C1 over 6. I hope you're enjoying my kids in the background. So now we have C2 in terms of our parameters, C3 in terms of our parameters. I'm going to do one more since I do have a C4 floating around up here. Let's find C4 in terms of our parameters. So I'm going to set that coefficient equal to 0. 12C4 plus 3C3 plus C2 plus 1/2 C1 equals 0. Okay, if I were to isolate the C4 here, C4 is going to equal 1/12 times negative 3C3 minus C2 minus 1/2 C1. And we want to put this entirely in terms of C1 and C0. I already have a C1 here, so I don't need to make any substitutions for that. But I have a C2 and a C3, both of which I have found in terms of C0 and C1, so I need to make a substitution for this guy and for this guy. This will come out to 1/12 times, now let's do this in our heads, so negative 3 times C3. Here's C3, I'm multiplying each of these terms by negative 3. That's going to turn that into positive C0 over 2 minus C1 over 2. Now I have negative C2. Here's C2, multiply everything by a negative. That gives me minus C0 over 2 plus C1 over 2. And then finally, minus 1/2 C1. We don't want to change that because we have a C1, which is what we're looking for. Notice cancellations happening here and here. That's going to be 1/12 times negative 1/2 C1, which is equal to negative 1/24 C1. Okay? Now, we can put this whole thing back into our original series. Remember, the goal is to find y. And I just found C0 through C4. So that gives me 5 terms that I can actually write out of this series, which is interesting. I'm able to get 5 terms, even though a lot of the work I was only dealing with 3 terms from each series. So with that, using what we just found, y is going to equal C0 plus C1x. Remember, these will be our parameters. We want everything in terms of C0 and C1. Plus C2x squared. But here is C2 right here. So I'm going to write C0 over 2 minus C1 over 2 x squared. And then plus C3 x cubed. But where is C3? This is C3. So plus negative C0 over 6 plus C1 over 6 x cubed. And then plus C4. But what was C4? It was this. Minus 1/24 C4 x to the 4th plus ... right? Okay. Now remember, the goal here was just to get two power series solutions, because then you could put those together to create a general solution. And we do that once again by setting C0 equal to 1 and C1 equal to 0 to get our first solution, y1. So So if C naught is equal to 1, then that constant term becomes a 1. My x term goes to 0, it disappears. This C1 over 2 goes to 0, leaving me with 1 half x squared. So I get plus 1 half x squared there. This term goes to 0, I get negative 1/6 x cubed, so minus 1/6 x cubed. And then, oh, that's supposed to be a C1 right there. C4 equals negative 1/24 C1. C1 is equal to 0. This entire term will drop out of this guy, so I'm just going to say plus dot dot dot. There's my first solution. Now we set C naught equal to 0 and C1 equal to 1 to get y2. So if C naught is equal to 0, I lose my constant term. If C1 is equal to 1, my first term becomes just x. And then here, 0 minus 1 half is minus 1 half x squared. Plugging a 0 in here and a 1 here, I get 1/6 x cubed, so plus 1/6 x cubed. Over here, C1 is equal to 1, and so this becomes minus 1/24 x to the 4th, and then that's all I have, so I can just say plus dot dot dot, okay? Those are my two solutions. And I'm not going to write it for this one, but I could say that my general solution is C naught times this series plus C1 times that series. Those give me the parameters that I need for a general solution. Okay, so we've done 3 examples here. That's going to be enough to show you what you need to do for the homework. This is a very, very long and tedious process. I admit it, and we just have to get through it. In Chapter 7, we'll look at a more interesting way and I think more efficient way, depending on the problem, of solving these types of problems. But that's it for 6.2.